Alrighty, y'all. So this next section, section 5.2, most of it's going to be review, which is going to be really nice. A lot of this you heard with Miss Spiller last year. So we're just going to do this section in a day. We're going to do it really fast so that you don't have to worry about it. So it's called the fossil record. First term we got here is fossil. It's a preserved remains or traces of an organism that lived in the past. Again, this should be a word that you know. It can be formed from bone, tooth, shell, or other parts of an organism. Excuse me, guys. It can also be footprints or burrows. Few are complete. It's usually only the hard parts, so you don't really get a fossil with every single bone perfectly intact. Normally, you get a fossil with most of the bones intact. But you're not going to get a fossil with all of the skin and all of the feathers and all of that. It's usually only the hard parts. Most fossils form when organisms die that become buried in sediments. So the organism dies, it gets buried in gravel, it gets buried in lava, it gets buried in what have you, and then that fossil forms within that cavity that builds up there. Sedimentary rock is our next term. It is layers of sediment that has built up. Petrified fossils is a third term. These are minerals that are dissolved in water that soak into buried remains. Gradually, the minerals replace the remains, changing them to rock. So think of cast and mold, which are going to be vocabulary terms coming up here. Excuse me. So they're soaking down into the buried remains of the organism, and then those minerals just replace those remains as those remains slowly deteriorate. So fossil record is our next guy. It's really continued. We're continuing. So mold versus cast. A mold is the hollow space in a sediment in the shape of the organism or part of an organism, while the cast is when a mold becomes filled in with hardened minerals. So mold versus cast. Again, these are terms you should know that you should kind of be remembering from last year. Preserved remains are our next one. These happen in ice, tar pits, or amber. A lot of people have heard about the big woolly mammoth that was found basically in a glacier. That it was baby woolly mammoth, and it has all of its skin. It has a bunch of stuff still left with it, which is pretty cool. This is the other portion of fossilization. Oh, right, amber. If you ever watched Jurassic Park, that's what the mosquito that they get the dinosaur blood is in. It is preserved in amber. Anyway, sorry. How to determine a fossil's age? We can determine in two ways. We have absolute dating and we have relative dating. Sorry, guys. So absolute dating is when we go in and do carbon dating, when we go and do potassium dating, all of that kind of thing. Relative dating is comparing the placement of the rock to placement of other rocks. Okay, so absolute dating is pretty straightforward. They check out the carbon and see how deteriorated it is or how long it's been since it was formed. Relative dating, though, now this is a picture of the Grand Canyon. Miss Spiller, myself, and Miss Olasso all went there a couple of years back, and we took pictures, if you remember Miss Olasso. But anyway, Miss Spiller was here too. You can really see how absolute dating works in this photo. So you can see this kind of big white line. This line is going to be younger than the lines below it, right? Because it's closer to the top than these bottom ones. And you can even see some smaller lines that go around through here, okay? So again, this is all about the relative dating. So relative to this big hunk of rock, we have this big hunk of rock. This one's older because it's lower, right? This guy is younger because it's higher. So older is lower, younger is higher. And some other random pictures. You can really tell this is the sandstone. This is the bright white line that we were seeing. You can see kind of the different types of stones in this it was like an indoor park type deal where you got a bunch of information. I don't even know what to call it. It was cool though. Anyway, it shows all of the different types of rock in that Grand Canyon. So this one says limestone. This is mauve limestone, red wall limestone, Watahomagee Formation. I don't even know what that. I hope I said that right. The Hermit Formation, Conoco Sandstone. So you can really see how different each layer is, and it's very easy to tell that this guy is going to be the oldest in the formation, and this guy is going to be the youngest. Pretty neat. There's Mr. Lost in the background, but anyway. You can see the different rivers, different tropical seas. You can see the eras that they find things in. So this is our Paleozoic era. This is like a supergroup of an era. This is a basement. So this whole Paleozoic era, you can see how it's spread out into different sections. And it's just cool. It's cool. Okay. And this is just the other side of the little doodad that we saw on the previous page. Miss Biller and her dog Pan is down there. If I stop moving my mouse, you'll be able to see him. Pan's pretty cool. Just a couple more. There's Pan. Just a couple more pictures from the Grand Canyon. Again, you can really see that sandstone up here. This is actually a Native American, I don't know what you call it, town, city. For the life of me, I cannot remember what it's called. I will post it in the comments on our slides later so that you can remind me, or so I can remind me of what it's called. I know it has a name. But anyway, they dug into this rock and used it as shelter to survive, right? It's pretty neat. Okay, sorry guys, moving forward. 2 random elk because they're cool. Alright, more fossils. So relative dating, again, scientists use this to determine which of 2 fossils is older. It's not going to give us an exact year, but if they know the exact year of the one above it and they know the exact year of the one below it, they can get a really good range as to what age it is. It can only be used when it's an original sequence. Oftentimes, we have this issue where we'll have fault lines and plate boundaries where the sequences will get messed up. So because these 2 plates are pushing towards each other, again, something you talked about in Earth Science last year, you had 2 plates pushing against each other. Sometimes one goes over the top of the other, and then it's no longer in its original sequence. So that makes it a little bit more challenging to figure out to use relative dating, right? Then we've got absolute dating. It's used to determine the actual date of fossils, so the actual age. It uses radioactive elements. These are unstable elements that decay or break down into different elements. So what scientists do is they know the original element, right, and they know the general quantity of that original element, and then they see it's unstable, right? They see how long it takes for that element to break down, and we know that time, right? 50% of the element decays in this period of time, 50% of the element decays in this period of time, and so on and so forth. So we can just take a big sample of it and find out at what decay rate we're at, if that makes sense. Half-life, this is the time it takes for half the atoms in a radioactive element to decay. So that's what I said about 50%. That's the half-life. So to see, again, half of the atoms decay, that's how we judge, right? That's how we figure out the date. Our fossil record are just the millions of fossils that scientists have collected. Nothing more than that, nothing crazy. It is incomplete. We do not have all of the fossils. Fossils are hard to come by. They're hard, they're challenging to make, they're challenging to I suppose you can't say challenging to make, right? They just don't happen often, right? The making of them doesn't happen often, right? When we bury people underground, they don't become fossils. They deteriorate. It takes rock, right? It takes rock to create a cast to then be filled in or just have that cast. So it doesn't happen often. So like I said, it's incomplete. We don't have every organism. We don't have all of the species of organisms. We don't have all of an individual species. It's incomplete. And hopefully this will go away in a second. The term extinct means no members of the species are still alive. Okay, so we could say a T-Rex is extinct, right? There's no members that are alive, unless you have some weird pets, guys. I really hope not. All right, moving forward. So how fast evolution occurs? When we talk about gradualism and punctuated equilibria. So this is just a scientific difference in trying to figure out which format happens more often, which format happens, they're just trying to figure things out. So gradualism, right, this guy, it proposes that evolution occurs slowly but steadily. So this is the evolution, this is time, this is our graph. So over time, it's saying that evolution is occurring very slowly all the time, right? So it's got this gradual movement. In punctuated equilibria, we say that species evolve during short periods of rapid change. So over time, right, evolution happens super fast, and then it stops happening for a while. And species 1 here just stays as species 1 for quite some time, and then all of a sudden there's a change in the environment, and the evolution, right, that's the line we're on, happens very rapidly again, and then that species stays the same for a period of time, right? Whereas we have that gradualism where it's happening all the time, but it's just a very, very slow rate. You get a really good view of this on page 158 in your textbook. All right, guys. So this is the end of section 5.2. At the end of this section, once you've gotten through all of this, once you've gotten through it, go ahead and turn to page 158. And why don't you guys do 1 through 4? Do 1 through 4 on the bottom of 158, and that will be your assignment for this section. Please know the vocab terms. There will be a quiz on them. Best of luck, guys. I know you've got this. Bye.